Hi, and welcome to Lecture 2, where we'll be talking about linear combinations of vectors, linear independence, and we'll also talk about matrices and matrix multiplication. Okay, so let's start with linear combinations. The definition. So, suppose we have q many vectors in Rn. Label them v1 through vq. A linear combination of these vectors is a sum that looks like this. Okay, so we choose some scaling factors in R, so real numbers. Okay, so we multiply C1 times V1 and then add it to C2 plus times V2 and so on. Okay, so something of this form is a linear combination of V1 through VQ. Okay, and these scalars, they're just numbers. They're also called weights sometimes. Okay, so that's the definition of a linear combination of a set of vectors. Okay, so let's see an example of that. So let's look at V1 being 1, 1, and V2 being 1, negative 1, two vectors in R2. So let's just generate a linear combination of those. So we can choose our C's as we like. Okay, so I'm going to choose C1 to be 5, C2 to be negative 1. Okay, so just plug in into our formula here. Okay, C1 times V1 plus C2 times V2. Working that out, we get that the sum is 4, 6. So what does that mean? That means that 4, 6 is a linear combination of V1 and V2. Okay, so instead of just generating a linear combination, let's ask the reverse question. Okay, so let's say I have V1 and V2, and I just choose a vector at random in R2. Okay, call that vector B. Okay, then I can ask, is this random vector B a linear combination of V1 and V2? That is, starting with B, can I find weights C1 and C2 so that B is a linear combination of V1 and V2? So that's the reverse problem, right? And unless the vectors are simple, it's not obvious whether it's true or not, or whether it's possible or not. Okay, so here's the question. Let V1 through VQ and a vector B in Rn. Okay, how do you determine if B is a linear combination of the V's? Okay, in other words, do weights C1 through CQ exist such that this equation here is satisfied? Okay, so we don't have the tools yet to answer this problem, but we will, and we'll come back to this. Okay, now just give a definition here. This is the definition of the span of a set of vectors. Okay, so what the span of a set of vectors is it's all possible linear combinations of those vectors. Okay, so this is the notation. So span of these vectors equals, okay, so this is set notation. So this means all vector sums of this form such that the C's are real numbers. Okay, so we fix our vectors V1 through VQ, and then we just let the C's range through all the real numbers, and then we'll get an infinite set of vectors over here. Okay. Okay, and one note that we'll say is that the zero vector is a linear combination of any set of vectors. Okay, because all you need to do is choose all the weights C to be 0, and then you'll get Q many zero vectors. When you sum that up, you get the zero vector. Okay. Okay, so let's look at linear independence of vectors now. Okay, so again, assume we have Q many vectors in Rn. And to determine whether this set of vectors is independent or not, we're going to write down this equation and analyze its possible solutions. Okay, so what does this equation say? Okay, on the left-hand side, we have the expression for a linear combination of the vectors v1 through vq, right? And on the right-hand side, we have the zero vector. Okay, so consider the vectors v1 through vq to be fixed. Okay, and the solutions we're looking for are going to come from the weights c1 through cq. Okay, so there's one immediate answer which will satisfy this equation regardless of what the vectors v are. Right? If we set c, all the c's, just equal to the number 0, then that will satisfy this equation. Okay, and that's called the trivial solution to this equation. Okay, so by analyzing the solutions, that will determine whether it's independent or dependent. Okay, so there's two possibilities. If the only solution to this start equation here is the trivial solution, that is every c is equal to 0, then the vectors are called linearly independent. Otherwise, if this equation has a non-trivial solution, okay, that means at least one of the c's is non-zero, then the vectors are called linearly dependent. Okay, so I have to look at this equation, analyze the possible solutions, and then conclude that the set of vectors is either linearly independent or dependent. Okay, so one fact you should be aware of is that any set which includes a zero vector is always going to be dependent. Okay, so here's how you can prove that. Okay, so let's suppose this is our set, and suppose that v1 is the zero vector. Okay, so v1 here is a zero vector. Okay, how can I come up with a non-trivial solution then? Okay, here's what I do. I set c1, c3, all the way up to cq, all equal to 0. So all of this goes away. And I set c1 equal to, say, 5. Okay, then it's going to be 5 times the zero vector, which is just the zero vector, right? So if the zero vector is among the v's, it's easy to come up with a non-trivial solution, and therefore that set is dependent. Okay. So let's think about sets that don't have the zero vector in it. Okay. Let's consider these two vectors. v1 equals 1, 2, and v2 equals 2, 4 in R2. Okay. Let's say we want to determine, are these vectors dependent or independent? Okay, so by the definition, that's equivalent to asking, does this equation have a non-trivial solution? Okay. Or filling everything in, does this equation have a non-trivial solution? Okay, so if you sort of stare at it a bit, you can probably find an answer. So here's the answer I got. So if C1 equals -2 and C2 equals 1, this will work. Okay, so plugging those in, I get the 0 vector. Okay, and that shows that V1 and V2 are linearly dependent. Okay, so as a note, this works because if you look at the vectors, V2 is a multiple of V1, right? If I look at V1 and I just multiply it by the constant 2, I'll get V2. Okay, so that's not a coincidence. And we have this fact here that if we just have a set of 2 vectors, okay, they will be linearly dependent if and only if one vector is a multiple of the other. Okay, so that's a fact you might want to try to prove on your own. Okay, so it's pretty easy to determine if a set of 2 vectors is dependent or independent, but it gets much trickier when there are 3 or more vectors. Okay, and this is another question we'll need more tools to answer, and we will return to it. Okay, so let's talk about matrices now. Okay, so a matrix is a rectangular array of numbers. Okay, and we'll consider them to be real numbers for now. Okay, so the size of a matrix is written like this: M by N, where M is the number of rows and N is the number of columns. Okay, so if we look at this example of this matrix A here, okay, so remember, rows are the horizontal lines of numbers like this, and the columns are the vertical lines like that. Okay, so A has 3 rows, right? And it has 4 columns. So A is a 3 by 4 matrix. Okay, so it's often useful when you think about a matrix to think about it in terms of the vectors that make it up. Okay, so we can think about A as its rows. Okay, so explicitly these are the rows of A. You can also think about A as 4 columns just placed side by side. Okay, so matrix is constructed by vectors placed beside each other in some way. Okay, so we can think of the rows as vectors in R4, right? Since each row has 4 real numbers ordered, that's a vector in R4. And the columns can be thought of in R3. There are 3 real numbers now, and they're ordered, so those are vectors in R3, right? And in general, if we have an M by N matrix, the rows are elements of Rn, and the columns are elements of Rm, just by the same reasoning. Okay, so here's a definition. Okay, so the transpose of a matrix is an operation that swaps its rows and its columns. Okay, so you've probably seen this. So if you have a matrix A, we notate the transpose by writing A to the power T, like this. Okay, so here's an example. Let A be the same A as before. Then this is the transpose of A. right? Row 1 is now column 1. Row 2 is now column 2. Row 3 is now column 3. Okay, so the transpose, you can think of it as sort of flipping the matrix along the diagonal. Okay, so take note that here A is a 3 by 4 matrix, right? And A transpose now is a 4 by 3 matrix. So the numbers are swapped. Okay, and that holds up in general. If A is an m by n matrix, then A transpose is an n by n matrix. Okay, and here we note the fact that if we do the transpose operation twice on a matrix A, you just get back A, right? That makes sense. Okay, so let's say what matrix addition is. Okay, so if A and B are two matrices, then the sum A plus B is only defined if A and B have exactly the same size. Okay, and we compute that sum in a straightforward way. We just add the corresponding entries. Okay, and here's a little example of the sum of two 2 by 2 matrices. Okay. And now I'll mention some notation we use. Okay, so in general, matrices are usually denoted or labeled with capital letters. Capital A, capital B, capital Q, and so on. As opposed to vectors, which are usually lowercase letters, right? U, V, X. Okay, so now I'll mention this notation. Okay, so this notation allows us to specify a particular entry in a matrix. Okay, so I have A, and I'm writing brackets around it. And in the subscript, I have I comma j. Okay, another way to write it is small a, and then in the subscript I comma j. Okay, this means the entry in row I, column j of the matrix A. Okay, so here's an example. Use that matrix A again. And let's say we write A2, 3 like this. Then what this means is we look at row 2, column 3, and we look at the entry in that position. Okay, it's 3 here, so A2, 3 is equal to 3. Okay, so let's talk about matrix multiplication now. Okay, first going to talk about how to compute a matrix A times a vector X, AX. Okay, so we're going to say A is some m by n matrix, and X is an n by 1 matrix. In other words, a vector. Okay, remember, every vector is a matrix that just has one column. Okay, so if I just gave you, say, a 3 by 3 matrix and a vector x of length 3 and asked you to compute A times X, you probably remember how to do that. And this is the method you would probably use. Okay, so this is called the row method or the dot product method. Okay, so how this method works is you think of the rows of A. So you think of A chopped up into rows. And then to compute AX, what you do is you take the first row, or the first entry of AX is the first row of A, dot product with X. Okay, so that's the first entry. And then the second entry is the second row of A, dot product with X, and so on. Okay? So that's sort of the standard way of multiplying. Okay. So here's another method that was probably mentioned to you in first year, but you probably didn't use it that much. Okay. In this method, method 2, so called the column method, we think of A as its columns instead. Okay? And what we do is we see that AX looks like this. Okay? We take the first column and we're going to scale it by the weight X1. Okay? Take the second column of A and scale it by X2. And so on, up to the nth column of A and the scale xn. Okay, so this is another method of doing it. Okay, so let's sort of see these two methods at work. Okay, so let's let A be this matrix and X be this matrix. Okay, by the first method, the dot product method, okay, we take row 1 and we take the dot product with X, and that is the first entry here. Okay, and then the second entry, we take row 2 times the dot product of X, and that's the second entry here. We compute this, and we get that this is the product AX. Okay, now we'll do the second method, the column method. Okay, so what do we do? What does it prescribe? Okay, we take column 1 and then scale it by the first entry of X, X1. So we compute this, plus column 2 scaled by the second entry, plus column 3 scaled by the third entry. Okay, so expand the constants into each column and then sum it all up, and we get the result here, 719. Okay, so we have two methods here, and well, as we expect, both methods give the same result. Okay, method 1 is a bit slightly better for quick calculations. Okay, it's usually a little bit less writing, and you can sort of do it in your head quickly. Method 2 sometimes takes a bit longer. Okay, so now I want to argue that method 2 is actually the better method for understanding what's going on. Okay, so why is that? Let's examine what's going on here. Okay, so remember, these columns are vectors, column 1, column 2, all the way up to column n, and we're scaling the vectors by some constants, right? What other word can we use to describe this, right? This is a linear combination of the columns of A, right? This is the exact form of a linear combination of a set of vectors, okay? In this case, the columns of A. Okay, so this method is preferred because it shows that matrix multiplication is really just taking linear combinations of columns of A. Okay, so that's the nice insight that you get here. Okay, the product AX is just a vector, and it's a linear combination of the columns of A, where the weights are coming from the vector X. Okay, so that's an important insight that this method gives. Okay, so we know how to multiply a matrix times a vector. What about a matrix times another matrix, and that other matrix isn't a vector. So we want to compute A times B. Okay, so let's let A be an m by n matrix, okay, and let B be an n by p matrix. Okay, so here's method 1. Okay, and this is probably the method you would use if you were asked to compute the product of two matrices by hand. Okay, so this is how you chop up the matrices. Okay, you think of the rows of A, okay, and you think of the columns of B, okay, and to compute the entry in row 1, column 1, you take row 1 of A dot product column 1 of B. Okay, and that pattern continues for the rest of the product, A times B. Okay, so in other words, when computing A times B, the entry in ij, okay, is going to be the row I dot the column j, where the rows draw from A and the columns draw from B. Okay, so that's the dot product method. Okay, we can also do another method. Okay, and so with this method, we don't need to use the dot product. Okay, so what we can do is consider A, and we're not going to chop it up yet, and consider the columns of B. Okay, so in this method, AB is going to be constructed like this. Okay, so the first column is going to be A times the vector column 1 from B. The second column vector of the product AB is going to be A times the second column from B, and so on, all the way up to A times column P from B. Okay, and then if we look at each of these column vectors, what is it? It's A times some vector. Okay, and now we can use our previous methods for computing A times X to compute each one of these columns. Okay, so again, method 2 shows you what's going on more clearly in terms of linear combinations. Okay, the dot product method up here is probably quicker for computations by hand, and there's less writing, but it kind of obscures what's really going on in terms of linear combinations, which is important. Okay, so let's observe this fact here, that before we said that A times any vector, the result is a vector, which is a linear combination of the columns of A, right? So that means that this column in AB is a linear combination of the columns of A. Same with all the other columns. Okay, so that's a good insight. Okay, and we've recorded that here, that each column of AB is a linear combination of the columns of A, okay, by the fact from the previous part. Okay, so let's mention the size of the product AB. Okay, so as you may know, AB, the product, is only defined when A and B are the right size. Okay, so let's suppose that A is m by n and B is a q by p matrix. Okay, so the product is only defined if n here equals q, if those two numbers are equal. Okay, otherwise, you can't compute these dot products, right? They won't have the same number of entries. You can't compute these columns and so on. Okay, you need n to be equal to q here. Okay, so if a and b is defined, if n equals q, then it has size m p. Okay, so if we look at this setup here, we have a times b. Okay, so to check if it's defined, we compare the inner numbers here, n and q. If they're equal, then it's good. That means AB is defined. And then the resulting AB will have size that's equal to the outer numbers here, m times p. So an m by p matrix.